Hi everyone, it's Mr. Baker here. I hope you're all well. Today we're going to be looking at the motor effect. Okay, so today we're going to be looking at the motor effect and we're going to be answering this question: how does an electric motor work? Okay, so here we've got a simulation from Focus e-learning, and what we have got is a magnetic field. So we've got two magnets here. We've got the North Pole facing down to a South Pole, and you can see that the magnetic field is going down and these green arrows indicate that. Then we've got these two metal bars alongside here, kind of this yellowy brassy colour here, and then this is completing like a circuit all the way around. So we've got a circuit, and when the switch is turned on, you have an electric current that is moving around through here. But actually what it will do, because this copper bar is on top here, the current will flow up and then along here, and so this will be the circuit here. So we'll have a current. So that means we'll have a current flowing through this copper cylinder that can move backwards and forwards depending on a force that it might feel. And that's really what the motor effect is all about. When you've got a current carrier that's in a magnetic field, it will feel a force. And so this demonstration shows you which direction it will feel the force in. So when we've got a current that's flowing this direction, so out of the screen, and a magnetic field that's going down, then you'll see that we have a force which goes towards the right. If I flip the current, and you can see what I've done here, is now the positive side of the cell is this direction, so the current is going to be going into the screen this time. When the current is going into the screen, the copper feels a force in the opposite direction. When I keep that the same, so now the current is going into the screen, and I'm going to change the direction of the magnetic field. So now the magnetic field is going up. It will feel a force towards the right. And if we reverse the current again like that, and we've got the magnetic field going up again, you can see it does that. So what we've seen is that when a current carrier is placed inside a magnetic field, it will feel a force, and we can change the direction of the force depending on the direction of the current and the direction of the magnetic field. Okay, so that's what the motor effect is. When a current carrier is in a magnetic field, it will feel a force, and the direction of the force will depend on the direction of the electric current through it and the direction of the magnetic field that it's in. We can actually predict the direction that that force will be felt, the direction that the current carrier will move, using something called Fleming's left-hand rule. So Fleming's left-hand rule can show us the direction of the magnetic field, the direction of the electric current, and then the direction that the current carrier will feel a force in. So here is a diagram of it. So if you try and hold your hand out like this, so you put your thumb straight up and hold your first finger out, so you've made like a little gun shape. Both of those are at right angles, and then put your second finger out again, so that it's at right angles to both of those. Then your left hand is in the right shape, and make sure it's your left hand. Okay, so in our diagram here, the thumb is showing us the movement. So let's not worry about that to start off with. The first finger is pointing in the direction of the magnetic field. So have your first finger pointing, say, into the screen. So your first finger is pointing into the screen. Your second finger is pointing in the direction of the electric current. And in this case, the electric current is pointing to the right. And so it's moving in the right. So that means that the thumb should be pointing up. And we can remember it with a mnemonic. So thumb with a capital M shows you the movement of the current carrier. Your first finger shows you the direction of the field. And then your second finger shows you the direction of the conventional current. And that's why I've spelled second wrong, and there's two C's in it. So second finger shows you the direction of the conventional current. So you can remember it like that, if you like, or you can also remember it using the symbols for each of those things. So B is the symbol we use for the magnetic field, I is the symbol we use for current, and F is the symbol we use for force. FBI, and you kind of made like a little gun, so choo choo choo, like a gun, like the FBI carry. That's another way of remembering it. Okay, so Fleming's left-hand rule can be used to predict the direction that a current carrier will feel when it's placed in a magnetic field. We're going to have a go at doing a few of these, so keep your left hand in that position and see if you can figure out the direction that these wires will move when they're put in different magnetic fields. Okay, so we'll start with a magnetic field across two magnets, north to south. It will go in that direction. Okay, so magnetic field, remember, goes from north to south. If we have a wire with the current flowing into the screen, then we should be able to predict that the force that's felt on that, see if you can do it. It's a bit difficult, you've got to kind of twist your hand around, is going down. Okay, did you manage to do that? Let's have a go at another one. So this time we've got our field. So first finger pointing from left to right, so it's pointing to the right. The second finger, the current carrier, is coming out. So the current's coming out of the screen. And so that means your thumb should be pointing up. So the force that's felt on the wire this time is up. Okay, so last one, look at this. So we've flipped the direction of the magnetic field. So the magnetic field is now pointing to the left. So point your first finger to the left. The current is coming out of the board. So twist your hand around. Your finger should be pointing out of the screen. And you should find that your thumb is pointing down. The force felt by that is pointing down. What you might want to do is just pause that video, replay that a little bit, see if you can use your left hand to figure out the direction of that. You'll look really strange in the exam while you're doing this. Everyone will be, if everyone gets to this question at the same time, you'll all be with your left hands out, trying to figure out the direction of a wire as it moves. It's normally only a 1-mark question, but it's worth just being able to practice that, make sure you know how to use Fleming's left-hand rule. So here we have a diagram of a really simple electric motor. We've got some magnets which make a magnetic field. Here we've got the magnetic field going to the right from north to south. Inside the magnetic field is a coil of wire. And we've got a power supply, and we've got that circuit there, and you can see the direction of the current going up to something called a split ring commutator via these little silvery sort of rectangles which are called the brushes. And we'll explain what each of those things do in a second. So here's a side-on view, sort of straight-on view of that same thing. And you can see when I turn the switch, the electric current flows through, and it flows through up to the brushes, or so up to the brush on the right. And when that brushes against the commutator, so that commutator is made of something that will conduct electricity, the electric current goes through that commutator into the coil of wire, around the coil of wire, back out through the brush on the left, and then it completes the circuit. Okay, so that's what the electric motor will do, and it will make the electric motor spin around. So an electric motor is taking the electrostatic energy and it's converting it into kinetic energy. So how does an electric motor start to spin? So here, if we get our left hands out again, so left hand rule, remember, Fleming's left hand rule says that we've got the magnetic field is our first finger. So if you point your left hand first finger towards the right, and we're going to have electric current flowing through the coil of the wire. And we're going to have electric current flowing through the coil of the wire. Let's do that again. So you can see when I flick the switch, what's going to happen is the electric current is going to come along here up to this brush. This brush is brushing against the commutator here. This commutator is attached to this part of the coil, and so the electric current comes up into the screen. So it's going around here, back out, and then completes the circuit. So the current will come from here up to the brush into the commutator, but you can see it's split, so the electric current can't flow straight across here. It's got to go into the screen here, into this coil. So it's going up on the right hand side here, it's going into the screen. So the current's going into the screen on this right hand branch of this coil, and then it's coming out of the screen on the left hand side, which then completes the circuit around here. So when we flick the switch, the current goes into the screen on the right hand side, and you can see we get a force that is pulling that right hand side down, and it's pushing the left hand side up. So it's starting to spin in a clockwise direction. So let's look at that. So this will be the motion that we'd expect. We'll carry on moving round and round in this direction. So how does it actually do that then? So the magnetic field acts from left to right. When the switch is closed, the conventional current will flow around the circuit and through the coil in an anti-clockwise direction. Meanwhile, the current goes into the screen in the right-hand arm and out of the screen in the left-hand arm. So using Fleming's left-hand rule, we can see that this would make the right arm move downwards, whilst the left arm would move upwards, making the motor spin around in a clockwise direction. The split ring commutator has an important job. It allows the electric current to switch off just for an instant. This is important because if the current always flowed in the loop of the coil, there would always be a force associated with the current in one particular direction. So if the current always flowed in this example, the right arm would always be forced downwards and the left arm would always be forced upwards. This would mean that when the motor turned 1/4, as it has now, it would stop in this position. So how does an electric current motor continue to spin then? So it doesn't just move 1/4 and then just stop in that fixed position. It carries on moving, doesn't it? And that's all down to this thing called the split ring commutator. With the break in the current that the split ring commutator allows, there is the break in the force. This allows the momentum of the motor to keep it spinning until the brushes touch the commutator again. When this happens, the arms are again forced into the spinning, so the electric motor continues to spin. Okay, so we've found out how we can get an electric motor to start spinning. We've found out how we can get an electric motor to keep spinning, but how can we make an electric motor move faster? So there are 3 things we can do to make an electric motor spin faster. We can put more electric current through it. We can use a stronger magnetic field, and we can have more turns on the coil. Any of these 3 things, if we do those things, then it will spin faster. Okay, so that's the end of this one. These are the things you should be able to do. You should be able to describe what the motor effect is. You should be able to describe how the force acting on a wire due to the motor effect can be increased. You should be able to apply Fleming's left-hand rule to determine the direction of the force acting on a conductor. And you should be able to describe and explain in detail the operation of a motor. So we asked at the beginning of the lesson, how does an electric motor work? And that's pretty much what we've answered in this lesson. Okay, so that's been our lesson on the motor effect and electric motors. I've been Mr. Baker, this has been another physics video, and I'll see you next time. Thanks very much.